Hello students, welcome back. This is the last video lesson for Module 12. This is not for everybody. We're going to deal with some highly unusual examples. 3 of them, as a matter of fact. All are related to applications of this formula. The derivative of the definite integral. How does it work? Well, plug in the first function, plug in the top function, the derivative, minus plug in the bottom function and the derivative. Here's a sketch of the proof. First, we begin with the fundamental theorem of calculus. Antiderivative function exists, so that capital F prime is f. So plug in the top and plug in the bottom, subtract one from the other. This is nothing more than just a fundamental theorem, except that here b and a are both functions. Early on, b and a are just numbers, but that's okay, it's just a substitution. What do you do now? We take the derivative now. And please pay attention here, we have to use the chain rule here. The derivative of this capital F of b, how does it work? By chain rule, the derivative of the outer function, that's step 1 of the chain rule. Now inside doesn't change, stays the same. Step 2 of the chain rule. And finally, the derivative of the inside. The same thing here, derivative of the outer function, inside stays the same, and then the derivative of the inner function. We use chain rule here and then chain rule there. And finally, make this observation. Capital F prime is small f, because they are original and antiderivative. So what do we get? We have this. Plug in the top function, the derivative, minus plug in the bottom function times the derivative. There are some special cases when one of them is constant, like these. The derivative of constant is 0, so that part drops out. Okay, remember those, and let's go over to highly unusual problems here. First, here we go. Find the equation of the tangent line of the following function at x equals to 1. How do we do this? Well, here's a strategy. What we want is y equals to m x minus x naught plus y naught, isn't it? This is an equation of the tangent line, the slope point equation of the tangent line. Here in this particular case, x naught is 1, so that's 1. Let's keep it as x naught. Y naught is f of x0, so this is f of 1. Next, what is m? That's f prime of x naught, so in this case f prime of 1. So what we need to do is find out y naught by plugging in x equals to 1 to the definition. Number 2, we have to find out the derivative function and then plug in x equals to 1. That's going to give me my slope. If you get the slope and the y-coordinate value y naught, and you can find out the slope point equation of the line. Keep this one in your mind, and let's go over to the answer key here. Step 1. y0. Plug in x equals to 1, and this is what happens. Plug in x equals to 1, the top part becomes 1 squared plus 1. So integral is going from 2 to 2. I don't care how complicated this integrand is. I'm not going to calculate the antiderivative anyway. It's not going to be possible, I think. Integral from 2 to 2, that's 0. That's always 0. So we have y naught equal to 0, 1 down, 1 more to go. Now let's find out the slope. How do we do that? We have to find out the derivative, and that's the key part. We have to use this rule here, this one here, and special case, this a is constant, so a prime is 0, so this part just drops out. And here we go. Actually minus 0. As a reminder, 0 part drops out. So plug in the top function and then the derivative. Okay, and I could multiply the derivative on the right hand side, but I decided to multiply here because this is a little bit simpler and a little bit more complicated. Okay, it'll work like that. Plug in x equals to 1 and simplify a little bit. It's not too bad. Plug in x equals to 1 and then simplify a little bit. You're going to get log of 6 over 6, so log of 1. And log of 1 is 0. So what do we get? In the end, we get slope is 3. So we got y0 value and we got m value. Put those together and we have the equation of the tangent line. The slope point equation of the tangent line. Okay, there goes one problem. Highly unusual, but there you go. Next, another problem that exploits the same kind of computation. This time, a limit computation. Now, the key observation that you have to make is that this is actually a 0 over 0 type limit. And let's rewrite this problem like this with a little bit bigger font. Okay, does it look better? This one we can move to denominator, and please note that this limit is 0 over 0 type limit. Plug in x equals to 2, what do we get? 2 squared minus 4. Denominator is 0. How about the numerator? This part is 2 squared minus 2, 4 minus 2, that's also 2. So this one, this integral here is integral from 2 to 2. So we have 0 over 0 type limit. So L'Hopital's rule tells us that once you have 0 over 0 type limit, you can take the derivative, which I did over here, and then here that's going to be the derivative. F of b of x times b prime of x minus, and then the a part is going to drop out because this is constant. Derivative of constant is 0, so that part will just drop out. Now what is b of x here? What do we have to plug in? X squared minus x, isn't it? So we have x squared minus x here. And the derivative, what's the derivative here? That's 2x minus 1. And that's what we'll have to do here. Okay. So what's the integrand here? Arctangent, okay. Put this arctangent here, except that this one is gonna be x squared minus x. I guess we are ready. Let's calculate this thing. We're plugging x equals to 2, so 2 times 2, that's 4. And this is 2 squared minus 2, and then this is times 2. Okay. Okay, this is times 2, so it's 4 minus 1, so this whole thing is times 3. Okay. And then this one is 4 minus 2, so 2 squared, this whole thing is therefore 4. And then 4 minus 3 is 1, so we're going to end up with arctangent of 1. What is arctangent of 1, by the way? It's going to be pi over 4. So we end up with, oh, we can finish it here. 3 pi over 16. And there goes the complete computation. We have an answer key over here, but this one I wrote here is a little bit better because of the bigger font. L'Hopital's rule. Take the derivative of numerator and take the derivative of denominator and then plug in the value. When you're taking the derivative of numerator, you have to use that fundamental theorem. That's how this problem works. Okay, finally the hardest problem. Determine the interval of increase and decrease of the given function, and it's given as an integral. Now, how do you determine intervals of increase and decrease? Find out the derivative and then find out the sign of the derivative. Positive derivative, increasing, negative derivative, decreasing. So that's what you have to do. Take the derivative and factor it. Now, taking the derivative of this, well, we'll have to use the fundamental theorem. And let's save some time. Let's go ahead directly to this. Take the derivative. That means plug in x squared plus 1 in place of y like this, and then times the derivative of the inside. Minus 1, that's constant here, so derivative of constant is 0, so we have minus 0. That part drops out. All we have to do now is work out this. When is it positive? When is it negative? Let's factor it out. So a little bit of computation, breaking of the parentheses, and then refactoring, and in the end, we have the full factorization. We have some quadratic irreducible part here and quadratic irreducible part here. They don't play any role. They're always positive. The key part, we have these three linear factors, x equal to 0, x equal to negative 1, and x equal to positive 1. That's when we have zeros, and their multiplicities are all 1, which means they're all odd, and we have to have sign change. In short, we have to have this kind of diagram. See, plug in real big X value, everything is positive, so increasing. Sign change, sign change, sign change, because they're all odd multiplicities. So we have decreasing, increasing, decreasing, increasing, associated to derivative, minus, plus, minus, plus. We have done these before. It's just that we have done this several weeks ago. This, by the way, is the graph, but this is a little bit difficult computation, even for Mathematica. We have a code here, but I don't know whether this is the most efficient code. Whenever I try to run this, it takes about 3 or 4 minutes. So I disable that computation. But if you really want to calculate, you can copy and paste and try. So what did you just do? We went through 3 highly unusual problems. Tangent line problem, L'Hopital's rule problem, and increasing decreasing problems, all associated to the fundamental theorem and the chain rule all over here. As I said before, this is not for everybody. Whenever I write this kind of problem, it's going to be a problem, and I intend usually less than 10% of the students get reasonably close, and usually about 5% of the problem, so less than 5% of the students get completely right. Is really special type of problem. So if you didn't really understand these too much, don't feel too bad about these. Now, if you're getting partly but not completely, maybe you're going to do a little bit of exercises on these, and I intend to write a quiz problem related to these, so please pay attention to those.